Okay, so let's talk now about basic features of operators. So we're talking linear operators on a vector space. So when you meet an operator, you have to have some questions, just like to get oriented about what are the basic properties of this operator. So if you meet somebody, you may perhaps ask where they are from, how old they are, some basic questions. And for an operator, there are similar things that you could probably ask immediately. And if you know the answers, you already know something pretty important about this operator. So we're going to be talking about basic properties of operators. Of linear operators. They're always going to be linear. And those basic properties, there are two properties or two characterizations of the action of an operator. So we have operators T that belong to LV, that is linear operators on the vector space V. And so what do we have? Associated to T, there is the null space of T, sometimes called the kernel of T. And this object is related to what is sometimes called injectivity. It's a property. So a property that characterizes this thing called the null space. We're going to explain all these terms. I'm just mentioning what are the basic things we want to talk about. So we have a null space. And then there's the other space that is interesting for an operator is the range of T. No other name for the range of T. And this is controlled by something called a property, or related to a property called surjectivity. So the purpose of this discussion now, what we're going to try to achieve, is give you a clear picture of what these things are, so that when you find a new operator and you know nothing about this operator, you may be tempted to ask what are these spaces. So let's begin with the first one, the null space of the operator. So the null space of T, null space of T is the set of vectors of T, of the vector space V, that are killed by the operator T. So it's the set of vectors V belonging to V such that T of V is equal to 0, the 0 vector. So there you go. That's a definition of the null space. Null associated to getting nothing out of this is, so what is being nullified or nullified by T is the things that are getting killed by T. This is a linear operator, so it might kill some vectors, and all these vectors form the null space of T. Now, what is null T? Well, it's a set of vectors, but in fact it's more than a set of vectors. It's a subspace of V. So it's a vector space itself. That means that, well, it's more interesting than just a set. So, for example, why is it really a subspace? Because if you have a vector in null of T and another vector in null of T, each one is killed by T, and the sum is killed by T. So the sum is also in null of T. Or if you have a vector killed by T, you multiply it by a scalar, and then that vector is still killed by T. So null of T is a subspace space of V. So that's pretty good. That's interesting. So now we need the other property, injectivity. Several names for injectivity. We'll see a few of them. So basically, what is injectivity? Injectivity is a property of an operator. We say that an operator is injective if the following doesn't happen. You take a vector and you act with an operator, you get something. You take a different vector, you act with the operator, you cannot get the same thing. You must get something different. So different vectors go to different things. So this is sometimes called the operator is injective, or it's one-to-one. And let me do a little picture maybe for this. So what is injective operators? That's what we want to define. So let me first say it as a definition. T, the operator, is injective if the following is true. If, whenever T on U is equal to T on V, we have that U is equal to V. So T of U equal T of V implies that U is equal to V. So if you get the same thing after acting on U and V with T, then U must be the same thing as V. So if you think of the vector space V like this blob, and here's another copy of V, you have two vectors here. This can go to another one. This does not happen. That these two different vectors go to the same thing does not happen if the operator is injective. So does not happen for injective operators, that two things are taken to the same thing. So with injective operators, everything is taken to something else. So sometimes people say that injective means one-to-one, as if one goes to another one and this other one goes to another one. So that's another name for injective. This is the word we're trying to define, sometimes called one-to-one. But there is perhaps a more perceptive way of saying this. I myself always found the expression one-to-one kind of unintuitive. Why one-to-one? Of course, T acts on one object and it gives you one object. So what does it mean one-to-one? Well, it doesn't mean two go to one. So actually, Sean Carroll, a professor of physics at Caltech, has said that the better way to say this is maybe 2 to 2. That's really more intuitive. If you have V and V here, and you have two vectors, well, then they go to two things. So this is like saying two vectors that are different go to two. That's a little clearer. You know, this does not happen, but this is injective, or 2 to 2. Two vectors going into two vectors. So another way to say this as well is that if it's injective, we have that T U, well, let me say it this way rather, U different from V implies Tu different from TV. So that's another way of thinking of injectivity. Two different things go to two different things, 2 to 2. And perhaps that's more intuitive. So look what we've done. We defined what we call the null space of an operator, and then we went ahead and talked about injectivity, a property of operators. Maybe they're injective, maybe they are not injective. So what is being called for now is a relationship between these two concepts. And the relationship is maybe clear. If the operator is injective, there's basically no null space. Nothing gets really killed. So let me say it more precisely. This is a little theorem, simple enough, but to prove in a couple of lines, but still worth stating. So T being injective is exactly the same as saying that the null space of T is just the zero vector, nothing else to it. So how would you prove this? It's kind of intuitive, but might as well try to say the right words and establish the concept. That's good exercise. I'm going to do it now. You could pause the video and try to do it yourselves. And however, as you wish. If we have an equivalence here, we're supposed to show that injective means that the null space of the operator is just the zero vector. You know, the zero vector is always mapped to 0 by any linear operator, so the null space of any operator contains the zero vector. But the null space is interesting if it has more than the zero vector, because there are many vectors that are killed by the operator. So suppose, let's try to go in this direction on the proof. Suppose T is injective. I want to show that the null space just has the zero vector. Well, we know the null space takes 0 because the null space is 0. 0 is taken to 0. But if the null space had more than the zero vector, then there would be some vector such that the vector is taken to 0 by the operator T. So if the null space was bigger than 0, there would be a vector that is also killed. But then you will have a situation where the operator is not injective, because two different vectors, 0 and V, are taken to the same one. So it's pretty much by definition that this null space cannot contain anything else than 0 if the operator is injective. So if this is true, it would violate injectivity. And therefore, it's not possible that the null of T contains more than 0. So there's no such V. V vector. So almost by definition true. How about the other direction? Suppose the null space of the operator is 0. So whenever something gets killed, it's the zero vector. So suppose you then have T of u minus V being 0. Since the null space of the operator is 0, the only possibility is that this vector is 0. So it implies u minus V is 0. And therefore, this equality actually means that Tu equals Tv implies U equal V. And that's what we called injective. Tu equals Tv implies U equals V. So you have here proven that this thing is injective going from this direction. So this is a pretty nice, simple theorem. It relates the words we've introduced. We've introduced a definition of a null space, a definition of an injective operator, and now it's clear how they are related. Now there's another this thing that we're supposed to discuss, the range of the operator. So what is the range of the operator? So let's go here. What is the range of T? Well, the range of T is the set of vectors of the form TV, where V belongs to V. So it's all the vectors you get by acting with the operator on the vector space. So you try acting with the operator T on all vectors in the vector space. Well, you get some number of vectors because it sends you back to the space, and that's called the range, the vectors that you get by action on the vector space. And again, this range of T begins, maybe we should separate this, begins as a set. It looks like a set, certainly the set of vectors that are of the form TV, where V is equal to this. But the interesting thing is that it's also a subspace of V. Think about it a second. If you have a vector that is in the range of the operator, means that it has been obtained by acting with T on some vector. If you add another vector that is also in the range, it has also been obtained by acting with T on the other vector. Therefore, by linearity, the sum is obtained by acting on T on the sum of the two vectors that were there before. So similarly, if you have a vector that is in the range, 3 times that vector is also in the range, because the original vector was obtained by acting with T on something, and the second will be obtained by acting with T on 3 times that something. So this is a subspace of V. And how about surjectivity now? What does surjectivity mean? Well, surjectivity is an adjective that we use to characterize operators that are particularly nice, and the operators that are an operator is said to be surjective if the range of the operator is really as big as the space you started with. So surjective means that by acting on the space, you still get the whole space. So let's write the definition. An operator T is surjective. T is surjective if range of T is equal to the vector space. So that's the definition of surjective. You reach the whole thing. So let's do a little example I think would be useful to make sure you understand these concepts. So this example concerns the operators that we introduced in a previous video, this left and right shifts. So you remember on infinite sequence, the left shift dropped the first element and kept everything there. And there is the right shift, and that pushed the elements to the right by adding a 0 at the beginning. So those are our operators. And we can ask, OK, nice to meet you. How about your null spaces, ranges, injectivity, surjectivity? What are the basic properties, the most elementary important things that these things do? So we can begin with L. Let's see, the null space of L. What vectors get killed by L? Well, those are the vectors such that here I get 0. Oh, so to get here 0, I can take x1 to be anything, but then I must put zeros here. So the null of T, of L, I'm sorry, now it's the operator L, is the set of vectors of the form x1, 0, 0, 0 everywhere. So it's a sizable null space characterized by one parameter. All these vectors are killed by L. So the null space is non-zero, so L is not injective. By our theorem, not injective. It takes several things to the same thing. For example, it takes the vector 1, 0, 0 to the same thing as it takes the vector 3, 0, 0. So it's not injective. How about is it surjective? Is any element in the range, is the range as big as the space? Well, the range is here. These are the things that I have. So if you present me a vector, I can get it. I simply put those inputs here and put whatever I want here. And then I'll get the vector you gave me. So any vector can be written as L acting on something. Any vector that I get, I can write as L acting on a number and the vector you have. So yes, it is surjective. L is surjective. So L is not injective, but it is surjective. And you might say, well, OK, that's pretty reasonable, but that's, in fact, quite counterintuitive. We will see soon. In the case of finite dimensional vector spaces, this thing doesn't happen. It's only because it's infinite. So let's see as for R, what is the null space of R? The null space of R is those vectors that get mapped to 0. Everything here must be 0. So if this is 0, all these numbers must be 0. The first one is, but if these are all 0, because the null space are the vectors that get mapped to 0, if these are 0, well, x1, x2 all are 0. So only the 0 vector is mapped to 0, because if you have any non-zero number here, it will appear here. So you won't get the 0 vector. So the null space here is just the 0 vector. It's the only one that gets mapped to 0. So if the null space is the 0 vector, this operator R is injective. And being injective is interesting. We can ask if it is surjective. Is this operator R surjective? It would be surjective if any vector in the vector space can be obtained as an output. But every output has a 0 here. So any vector in the vector space that has not a 0 in the first entry cannot be obtained by acting on R. So R takes the vector space and, as it acts, produces something smaller than the vector space, a subset of vectors in which the first entry is 0. So R is not surjective. So that gives us an idea of what's going on here. Now, we've identified a few properties here, and now we're going to say something more about these operators. We want to discuss a basic result, and it's, in fact, a very fundamental result. I will not quite prove it, but will come close to proving it, close enough that I think you could complete the proof without difficulty. So I will put that in here, and we'll claim that there's something quite interesting that relates the null space and the ranges for finite dimensional vector spaces. So you can consider the null space of the operator, null of T, and the range of T. And you can say, well, the null space is a subspace, so it has some dimensionality. Maybe it's 0-dimensional if the operator is injective, but perhaps it's bigger. So it will, in general, have a dimension. Well, the null space and the range, in some strange way, complement each other. It's a little strange, as you will see. But here it is, the dimension of the null plus the dimension of the range add up to the dimension of the vector space that you started with. So this is applicable to finite dimensional vector spaces. The dimension of the kernel, or the null space, and the dimension of the range add up to the dimension of the vector space. It's a very nice and interesting theorem. In fact, it's more general than the way I've stated it here, in that if you have a linear operator that maps from a vector space V to a vector space W that is different vector space, this still holds even though the null space of the operator, if you would have a V going into a W, which is not what we're doing now. We're talking linear operators from V to V for this holds. But this theorem even holds when you have a vector space and a map to another vector space. And then it's kind of maybe surprising that it's so powerful, but at the same time, it leads you to a clearer thinking of this property because it doesn't depend on V going into V. So in that case, the null space of the operator is a subspace of V, and the range of the operator is a subspace of W. And still, funnily, this dimension and that dimension, the dimension that gets killed here and the dimension that you reach here, add up to the dimension of the total vector space. So it's a very nice theorem. How would you go about proving it? Basically, what you would have to do is the following. You start with a sketch of a proof. I will not do it, but I think it's a good idea to just even imagine what needs to be done. Think of the vector space V and the null space. these are the vectors that are killed by the operator. This is a vector space, vector subspace of V, and therefore there is a basis for the null of T. So a U1, U2 up to U, say, N, forms a basis of the null space of, let me do M, and this is a basis for null T. It's a vector subspace of V, therefore this is still a basis for the vector space V. But it's not the full basis because the null space might be much smaller than V. So if this is a basis for null, they are linearly independent, certainly within V, and therefore it can be upgraded to a basis for the whole vector space by adding vectors V1 up to V, say, N. And then you would have a basis for V. So your task would be to show that from these vectors, the TVI, the set of TVIs, are a basis for range of T. So if that is the case, if you can show that these remaining vectors that are needed to form a basis of V are a basis for range of T, then you would have that the whole dimensionality of the vector space is the number of vectors here plus the number of vectors there. That's the dimension of null plus the dimension of range. So that would prove the result. And it's not that hard to do that step. And you may enjoy thinking about it. So this is a main theorem, and we'll illustrate it with one example here. So kind of a degenerate example. Is not that complicated. An operator T of the form 0, 1, 0, 0. Lots of zeros. So it's a kind of strange operator, of course. It's not invertible, and it's funny. So, but it's good because you can be very concrete here. So let's consider the null space of T. Well, what is the null space of T? Are those vectors that are killed by T. So let's act on a 0. Let's do the calculation. How do we do it? We put the matrix, we put an arbitrary vector. We see what we get. You get B and 0. And we demand that this be killed, because we're asking for the vectors that are killed by T. This is a vector. Acting on T is this. You want it to be 0. So the vectors killed by null T, killed by T or in null of T, are vectors for which B is 0. This component is 0. So are vectors of the form something here and 0 there. These are the vectors that are killed by the operator T. So the null space, this set of vectors is spanned, is equal to the span of E1, what we usually call the vector E1. E1 being the vector that has a 1 in the first component and a 0 there. So the null space of T basically spanned by E1. All right. So how about the range of T? To calculate the range of T, you would begin with the operator and act on a general vector. So you would have 0, 1, 0, 0, acting on AB. And see how much you can get. It's the same calculation. And you get B 0. So actually, the range of T is the range of T. And here's where it can get a little funny. The range of T is this kinds of vectors. Those are the vectors that you can get. These are the most general vectors that you can get after action by this operator. So the range of T is again something with this form. So the span of E1 you say, that's funny. The range is the same as the null, or what's going on here? But you shouldn't get confused. The range of T is this, and look at what the theorem was supposed to be telling you, that for the vector space you have a basis for which you have some vectors that are a basis for the null, and some vectors which, acted by T, are a basis for the range. So actually, if you have E1, E1 is really T on E2. Why is that? Well, T 0, 1, 0, 0 on E2, 0, 1. That gives you exactly 1, 0. So indeed, for the vector space, you have a basis. And there's E1 and E2. And this is a basis for null of T. And the second vector is such that T of E2, which is E1, is a basis for the range of T. So it's true that the range is the same as the null, but that's not a contradiction. What you really need is that the basis of the space is such that the nulls form a basis, and the rest are such that acted by T are a basis for the range. And that's exactly what's happening here. The range is also equal to E1, but E1 precisely is equal to T E2, and therefore T acting on the second basis element produces a basis for the range, and that's why the theorem holds. So this is our main introduction to these key properties of null space, range, injectivity, one-to-one, surjectivity, and it's the first thing you always do when you meet a new operator.